Welcome to Pre-Calculus. Today we will investigate various discontinuities in functions, focusing on classifying discontinuities as jump, infinite, or removable, as well as finding limitations of graphing calculators in the way they represent discontinuities. Let's take a look at 3 total examples. We'll begin by looking at one example. Let's head over to our notes page. And I want to repeat the 3 possible types of discontinuities, give a brief definition of each one, and then just sketch an example so that we can see it graphically. So the first discontinuity that we see here is a jump discontinuity. So a function has a jump discontinuity. We'll write this definition. A function has a jump discontinuity if the left-hand limit does not equal the right-hand limit. If the left-hand limit does not equal the right-hand limit, so there's something about the discontinuity where one side does not equal the other side, and both sides are finite or have finite limits. So there's some words, and what I'd like to do is offer just a brief sketch to illustrate what this would look like in a graph. So we'll put an example here of a function that has a jump discontinuity. So let's sketch part of a parabola. And down here, I'm going to say that this ends. So we're not going to look at the whole parabola. We'll say that it kind of ends there at x equals 1 and has the y value of 1. So that point there at the end is 1. In fact, we'll write it as a coordinate pair, 1, 1. Now, it would have a jump discontinuity if I saw something like the graph picking up again somewhere above it. And let's say this side is a straight line. And we'll label this point here above as the point 1, 3. So what we're saying in terms of the left-hand limit not equaling the right-hand limit, this y value doesn't equal that y value, even though they have the same x values. So as x approaches 1 from the left side, it would get closer to positive 1. As it approaches from the right side, it would get closer to 3. 1 does not equal 3, and that would indicate a jump discontinuity. And in terms of the graph, it looks like there's some gap in the graph, but both sides come to some finite number. So the lower one comes to the 1, the upper one comes to 3. Well, that's a jump discontinuity. Let's define also an infinite discontinuity. So a function has an infinite discontinuity. We'll write this. And see if you can predict what would be different between jump discontinuity and an infinite discontinuity. So a function has an infinite discontinuity if the left-hand limit does not equal the right-hand limit. So all of this is the same. The left-hand limit does not equal the right-hand limit. So what do you think is going to be different between the two? Right-hand limit, and both sides have what kinds of limits? In fact, in both or one side. Excellent. Excuse me. You get excited about limits, have infinite limits. So the main difference is in one word there. The jump discontinuity is between two sides that have finite limits. The infinite discontinuity is where the two sides have infinite limits and they're not equal. Well, let's again sketch an example so that we can see. So what we're looking at is, for instance, a rational function that has a vertical asymptote there. Let's say that that's at +1. And the graph itself would be here above the x-axis and over on the right below the x-axis. So if we look at the left side as it approaches this value of 1, it's going towards infinity. As it approaches 1 from the other side, it's going towards negative infinity. And you can see the difference in the graphs. The blue one, the jump discontinuity, they end in points, either closed or open points, whereas an infinite discontinuity, it's going up forever, like we saw with end behavior. So those two are discontinuities which would prevent us from taking a limit. Let's see what this removable discontinuity looks like and how it's different. So the removable discontinuity, a function has a removable discontinuity. And see if you can predict, just thinking about what could be different between graphs, given that we've defined jump discontinuity and infinite discontinuity. A function has a removable discontinuity if the right-hand limit equals the left-hand limit. So this is different. If we'll start with left-hand limit equals the right-hand limit, but not the function value at that point. But not the function value at that point. So those again are some words. Let's see what a graph that has a removable discontinuity might look like. So let's consider, we'll sketch a graph here. Let's consider a parabola again. We'll turn this one so that it's headed downward. And what we want to do with a removable discontinuity is we want to say that there's some gap in the graph. So let's say that here at x equals 2, there's a hole in the graph, and at that point, in terms of the function, is really up there. So we've got a point, let's say it's 2, 3, but the point on the graph itself would be 2, 1. So essentially what we're saying with a removable discontinuity is I've got some gap in the graph, a tear or a gap, where I can see that the limit should be at 1, even though the function value's here at 3. So 3 examples to illustrate these 3 categories of discontinuity: a jump discontinuity, an infinite discontinuity, and a removable discontinuity. Let's take a look at one example to begin here. So like we've done, we want to start off by graphing each function by creating a table of coordinate points. And what I want to notice as I start to graph this by creating the table is that I really have 2 functions in one. So I'm going to put the x column here. And what I've got to see is that one function is when x is less than or equal to 2. So I'm going to pick up the values -2 through 2. And those will be for this exponential function, 2 to the power of x plus 2. Now, when we reach 2, we come under the influence of a second function. So this one is 1 over x plus 1. So it's a rational function. And it really starts when x is bigger than 2. So it wouldn't include 2, but it would include 3. We'll go 4, 5, and 6. Let's give a name to this kind of function. When you got different pieces to one function based on the x values being partitioned like this, we call this a piecewise function. Piecewise function. It's piecewise. So let's take a look at our functions in the graphing calculator. So I'm writing down this piecewise function, 2 to the power of x plus 2, 1 over x plus 1, and I'm going to enter that into Desmos. So I'm headed over to the graphing calculator, and I'll start by saying f of x equals that first one, so 2 to the power of x plus 2. And then I want to give a space, and I'm going to type the curly bracket, and I'm going to say that restriction. So x is less than or equal to 2. Then I'm going to close the curly bracket. And notice how it stops the function right here where x equals 2. Let's type in the second half of the piecewise function. I'm going to call this g of x just to allow the calculator to treat them as two pieces. So that one was 1 over x. Hit right to get out of that denominator, plus 1. And again, the restriction on the x is greater than 2. And what we're seeing is that that second half of the rational function on the right shows up starting from 2. Now I want to get a table, so I'm going to hit the cog, and then I want to graph this first function. So we're going to take it -2 through 2, and we'll record those values so we can see them approaching here on the left-hand side of this purple graph. -2 is at 2 1/4, -3 is at 2 1/2, 0 is at 3, 1 is at 4, 2 is at 6. We'll also create a table for the second half of the piecewise function. And notice how it's showing up on those values of x that are lower than 2, undefined, 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 undefined. So what I need to do is put the values that are within the domain of this second right-hand piece. So 3, 4, 5, and 6. So notice those points are showing up again. We can see that at 2, the function's not defined. Now here's one of these pieces that the calculator has a hard time representing the discontinuity. It looks like it's actually existing at 2, but when I click on the graph, it tells me that at 2 it's undefined, because for that right piece, it only comes into effect when I'm greater than 2. So if I go bump to the right just slightly, all of a sudden I have values. Now it looks like that value at 2 is around 1.5. But again, I can't say that that function exists at 2 because of the restriction on its domain. It is strictly greater than 2, if we saw the way that we typed it in. And then as we head on, 3 has a value of 1.3 repeating, 4 is at 1.25, 5 is at 1.2, and 6 is at 1.1 repeating 6. Okay, so that gives me what I need from Desmos. I'm going to go and fill in our table here. So for the exponential function, again, it was 2.25, 2.5, 3, 4, and 6. And then this function didn't really have a value at 2, because remember, it's strictly greater than 2, but it was about, if we go to the slight right of 2, 1.5. So I'm putting in parentheses. And then at 3, it's clearly 1.3 repeating, 4 is 1.25, 5 is 1.2, and 6 is 1.16 repeating. So we'll graph those two pieces of the piecewise function. So -2 is at 2 1/4. -1's at 2.5. 0 is at 3. 1 is at 4. And 2 is at 6. Now I'm going to emphasize that point on the right. We'll go ahead and graph this. So no arrow there on the right. There is an arrow on the left. And then we're going to pick up with that lower function with its coordinate point. So 1.5 about at 2. But to indicate that it doesn't actually exist there, I'm going to put an open circle. At 3, it's 1.3. 4, it's 1.25. 5 is 1.2. 6 is 1.16. So it looks like we got a vertical or a horizontal asymptote here. I'm going to do that in green, where this is getting closer and closer to the y value of 1. So we've graphed the function by creating a table of coordinate points. Now we want to classify the discontinuity as a jump, an infinite, or removable discontinuity. So recall the way that we had defined those three. We'll go back up to our definitions. Jump discontinuity is if I've got finite limits from the left and from the right, but they're not equal. Infinites if I've got infinite limits not equal. And a removable is if the limit's there, but at that point the function has a different value. So I'm looking here, if I investigate here, so I've got the point 2, 6. This point here is 2, 1.5. These are finite, and this would indicate a jump discontinuity. Again, remember, jump discontinuity says these are not equal, but they're finite. They're not going forever to infinity or negative infinity. Okay, so I'm going to pause there. We've got 2 more examples to take a look at, but I want you to give a chance to go graph and categorize some of the questions you're working on. Thank you for joining, and we'll be back in just a moment.